Okay, so let's start the class. So most of you did very well for test number 3. So that made me very, very happy. Okay, so I hope you're gonna do as well for the final. Okay, so as usual, lot of conceptual questions, a few numerical questions. And do remember that the final is on the first day. So it's like lundi, mardi, mercredi, jeudi, 22, 23, 24, 25, 25th, April 25th, right? So make sure you don't miss it because after that I have to upload all the grades for those who are graduating. So having a makeup will be very difficult for me. So and for you. So make sure you don't miss it. It's gonna be in person on paper. Make sure you print out, not only the equation sheet, but the last page of those units. So it's going to be more on the last things that we will be doing, like Faraday's law of induction and whatever we're going to do after that. Okay, so conceptually heavy. Okay, so I was very happy. For test number 3, I'm late for posting new assignments, so I apologize. I feel I'm gonna try to do it today for next week. And as usual, if you need extension, I will give you extension, but try to be on time. Okay, so last time I want to go back to these slides here where I try to summarize everything because electromagnetism is very heavy in conceptual principles, so it's hard to digest everything. I may have said something wrong, so I want to make sure I didn't say anything wrong. You see, you can think of the magnetic flux as being the number of field lines poking through, okay, poking through like a membrane, even though it's like imaginary membrane that you attached here to a path. So for example, if you have a conductor, so if you have a loop, okay, so let's say you have a loop made of copper wire in your head. You can imagine that you have a membrane here attached, and the flux will be the number of lines poking through. So here the flux is maximum, here the flux equals to 0. The flux is again maximum, but if you take an orientation to your area, then the flux is going to be negative. But you don't have to worry about that. Okay, so imagine you have a loop here and you rotate it inside that magnetic field. The flux is going to change with time. So you're going to induce a current. Okay, so the flux is maximum, the flux is going to decrease. Okay, so you can see that actually the flux, okay, equals to the magnetic field strength, of course, because if you have a stronger magnetic field, if you have a stronger magnet or electromagnet, you're going to provide more magnetic field lines. It will be proportional to the area. Of course, if you have a large area, you're going to catch more of those lines, and it depends on the angle here. Right? So if the angle is 90 degrees, you are not going to catch anything. Is that clear? Okay, so I like to go over that again. So Faraday's law of induction, you have a induced EMF. Okay, that induced EMF will be equals to the rate of change of the magnetic flux. Okay, so the number of lines poking through the membrane attached to your conductor has to change with time. So we already discussed that. You can have here the equation for the flux equals to the number of loop, the magnetic field strength, the area, and it depends also of that on that angle here. Okay, so you can see the angle here. Somewhere under the rainbow. No, here, right? That will be the angle. Okay? Any question? Don't space out because concept is very important. Okay? So, for example, in that case, you see those magnetic field lines are poking through, okay, this area here that you can attach to the loops of the coil that make up the coil. Okay, So you go out, you go in, you go out, you go in, and you're going to induce a AC voltage, okay? AC current. That comes from your book, Johnson and Continental. And again, you have the explanation. So that's why if you want to print out this page here at the end, so that will be at the end of here. If you want to print out this page here, write that down somewhere. No, I'm just not at the right. I have too many things open. So you see at the end of this unit, okay, so that will be the unit 3.2. You have a summary. No, that's not the right one. This one. Okay. Here you have a summary of Faraday's law of induction. So you have all your equations with the explanations. So I highly recommend that you print out this page and the page from 3.1 and the page from 3.2 in addition to your equation sheet, and make sure you get used to those equation sheets, okay? So you can see through the equations, and the day of the final, you don't bring your grade down, okay? That will make me very sad, and I don't like to be sad. Okay. Okay, and then we talked about AC generator. So in a powerhouse, so you have a closed loop here. So that end will be attached to the load. That means attached to the high tension line and then to your house. Okay, so the idea is that you're going to rotate that coil, usually it's a coil, okay, inside a magnetic field, uniform magnetic field, and you're going to induce a AC voltage. Okay, so the voltage will be AC. You see, that's going to be the peak voltage. So in the US, the peak voltage is going to be 170 volt, and the RMS will be about 120 volt. Okay, you take the square root of 2, you take 170, divide by square root of 2, and you have the RMS. But this value here will be the peak value. Omega, okay, will be the rotation speed. So it will be, say, revolution per second. So for the pop quiz, I'm going to have equations on that. So it will be revolution per second. So for us in the US, the speed will be 60 rotations per second or 60 revolution per second, which means that the frequency is 60 hertz. The period, okay, so the period is the time for one cycle. It will be 1/60. Okay, so we already talked about that. You see, omega is like a speed. A speed will be the angle here in radian divided by the time. So that will be the time for one revolution. So 2 pi is one revolution, and t is the period, is the time for one revolution. Is that clear? So again, the unit for it doesn't work. It doesn't work because it's upside down. Yeah. So the unit for omega, which is a speed, okay, the unit for omega is rad per second. What you see here is an angle, right? Because omega will be the angle in rad divided by the time. So if you do one revolution, okay, it's going to be 2 pi. The time for revolution, it will be always the same because you have a uniform speed. It doesn't speed up or it doesn't slow down. It's moving, it's rotating at a constant speed. So this is your angle here. Okay, that angle here, actually I show you what is that angle. That angle here will be the angle between the magnetic field and this vector here perpendicular to your membrane attached to your loop. Is that clear? So I want to make sure it's clear. That peak voltage here for us in the US, it's about 170 volt. In the US, omega for one revolution, it's going to be 2 pi over the period, which is the same as 2 pi times the frequency. So in the US, that's going to be 2 pi times 60. So 2 times 60 is 120. So 120 pi. Okay. So the equation, okay, for here, for the outlet will be 170 sine 120 pi and time. Okay. So it means that if you were, I already showed you last time a small demo with a mini oscilloscope. If you have an oscilloscope and you were able to plug that into the outlet, you're going to see a sine function. Okay, I say it over and over and over and over again. That's going to be your peak here at 170 volt. And then you have some kind of average here. We call that the RMS, which is 120 volt. You see that 120 is 170 divided by square root of 2. That value here, that's what you measure with a voltmeter. Okay, so if you plug that into your outlet here, you're gonna read 120 volt AC. You don't read the peak voltage. Is that clear? So again, what do we call the period? And that's going to be useful because we're going to talk about wave next. So you see, that's one cycle. One cycle is the period. And in that case, the period is 1 over 60, which is about 0.017 seconds, something like this. Is that clear? So 60 hertz means I have, in 1 second, I have 1 cycle, 2 cycle, 3 cycle, 4 cycle, blah, 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 blah. 60 cycles in 1 second. Okay? Isn't that interesting? You know how we produce electricity? Okay, so I try to summarize here everything. What else did I wanted to talk about? Okay, let's talk about the transformer again. So when you apply a AC, I found a nice simulation. So let me try to find it here. So here you have an AC power supply. So you see the current is going to flow in one direction and then it's going to flow in the other direction. So here, because you have a solenoid, you have a coil, you see the magnetic field is going to expand, collapse, right? So you're going to have the south here, and then here you have the north, and here you have the south, because it's AC. So a transformer will work only with AC. So if I try to trick you and I say, okay, I have DC here, can I get something there? No, something has to change. Okay, so you see here the magnetic field expand, collapse, expand, collapse, but you see it's always reversing each other. So here, this is called the primary coil, and this is called the secondary coil. In that secondary coil, you're going to attach it here to a load, for example, or a voltmeter. So here you have no power supply, but because the magnetic field is going to change with time, it's going to induce an EMF, induce a current in the secondary coil. Isn't that amazing? Very interesting, right? And you see that number of lines poking through the membrane increase, decrease, increase, decrease, increase, decrease. And because here you see the magnetic field goes up and down, up and down, up and down. So the current here induced will also be AC. Isn't that a nice animation? Right? See that? So here you have your power supply. So it could be your turbine. Okay, so in a powerhouse, you have a turbine. You make it spin because you are burning fuel. Let's say you are burning coal. Okay, so you burn coal, you burn water. Water goes into steam. Steam will make your turbine move. Okay, so you're going to produce about 20,000 volts. And then you use a transformer to step it up to about 100,000 volts until it gets to the city. Then you're gonna step it down and then step it down again until you get 120 volts. So let me show you another one. So the thing to understand here is that when you are using a transformer, it looks like that. This is made of soft iron and it does not let the magnetic field escape. It's going to trap the magnetic field here inside that donut made of soft iron and it will amplify it. Okay, you don't let it escape. Okay, so you guide the magnetic field through this membrane, imaginary membrane. So you see the number of lines is going to increase, decrease, increase, decrease, increase, decrease, and that's how you can induce a voltage. Is that clear? I'm very proud of myself because I found all those GIF. You could not find them, like it's something new, right? So when I started teaching like 20 years ago, I didn't have slides. We had like transparency, you know, those things that you put on the, remember those? So for me, it's like, phew, it's even better here. So anyway, example, let's say you have 10 loops here and you have 40 loops there. So that will be your input. That's going to be your output. Okay. Output will be connected to a load. Okay. So on that side, there is no power supply. You have only power supply on this side. Okay. So again, it's going to be AC. So the magnetic field is going to flow in one direction, the other direction. So as long as it's changing, you're going to induce here a voltage. So if the number of loop is multiplied by 4, okay, that's going to be a step up voltage. So that means if you start here with a voltage of 12 volt, what's going to be the voltage here? You multiply by 4, it's going to be 48 volt, right? But there is no free lunch. So that means if the voltage goes up, the current has to go down. Okay, so you don't violate the conservation of energy. So that means if you have 1 amp in the primary coil, you're going to have 1 divided by 4. And 1 divided by 4 is not 0.4. That's a typo. Shame on me. Right? 1 divided by 4 should be 0.25 amps. I have to fix that. So the current will be divided by 4. Okay, is that clear? So if you find the power, so the energy, okay, produced per second is going to do 12 times 1 is 12 watts. And if you do 48 times 0.25, it's also 12 watts. So power in has to be equals to power out. Okay? Is that clear? Okay, it's not easy to understand because you have to, it's very abstract. Okay, and then I want to go back to this one because I'm not sure it was clear. So this is also like a transformer, okay? But now you have, it's called a toroid. So I already show you one, but you see it has a shape of a donut. So for example, if you apply your power supply and you have your coil, okay? So here you have your core. It's also made of soft iron. So it means that when you're going to connect your coil to the power supply, the magnetic field is going to expand, but here we have DC. The magnetic field is going to be trapped inside, okay? It cannot escape. It will be amplified. Now, if I start to connect it to a AC, okay, so that magnetic field is going to, same as a transformer, is going to expand and then collapse, expand in the other direction, and then collapse and expand in other direction. So it's going to induce a voltage in this circuit here. So exactly like a transformer, except it looks like a donut. It's called a toroid, and it's used a lot in computers, right? They use them to filter out high frequency noise. Okay, you can use, it's called a conductor, you can use them to filter out the noise. By the way, let me show you what it looks like. So that's my calculus class. It looks like this. So here you have a motherboard, okay? You have those inductors, it's called the inductors. You see here it looks like a solenoid, it's also an inductor, and you can use them as a way to store energy inside the magnetic field, or you can use them to filter out high frequency noise, or you have other application for them. So it's called a toroid. Why do I talk about that? Because that was the original experiment done by Michael Faraday. I admire a lot Michael Faraday. He didn't go to school. He taught himself science, and he's the one we have to thank for electricity. Okay, that's what we have today. So in his experiment, you see here, okay, he had DC because Tesla was not around at the time. But when you close the switch, magnetic field expand. So on the other side, you're going to see a change here, and then no more change. When you open the switch, the magnetic field is going to collapse, but it takes time for the magnetic field to collapse. So there will be a change here, okay? The number of magnetic field lines will change. So you also see a change in the meter and EMF. Is that clear? Okay, so even if you have a DC circuit, when you close the switch, just during that time, or open the switch, the magnetic field expand. So the number of lines are gonna increase, and then it's stop, it's constant. When you open the switch, the magnetic field collapses, so the number of lines decreases, and then it stop. You don't have back EMF anymore. Is that clear? I think I had another GIF. Let's see if I. This one, look. So turn off, turn on. So this is an electromagnet. So you see, it takes time for the magnetic field to build up. So only during that time here, the number of lines are going to increase, and you see EMF induced. Or when it's going to collapse because you turn off your electromagnet, you're also inducing an EMF. Only when you turn on the electromagnet or turn off the electromagnet. So that's why if you're listening to a radio or you have some kind of electronic appliance, you unplug, never do that, okay? You unplug and it's still working, right? Because it takes time for the magnetic field to collapse. So that's why. And those things can be very dangerous, not as much as the capacitor, but because it can store energy into the magnetic field when it collapses, it can produce a spark. That's how Tesla coil works. So anyway, that's the original experiment by Michael Faraday. And you see at the time he didn't have like insulated wire like we have today. You see you have plastic here to insulate the wire. Instead, he used fabric, and his donut was way bigger than the one that I'm using. Okay, any question? Yes.
So, before, like when I like charged my phone, and then like unplugged it from the wall, my phone would keep charging for a few seconds. That's the magnetic field.
So
Is that
it's the same idea. Maybe it's like more like the capacitor. Okay, I have to do research on it, but it's the same idea, right? So if you listen to radio, for example, you unplug like this, it will still be working, right? So for the phone, it has to do with the same idea, okay? Because capacitor, inductor. So a capacitor, it's going to store energy into the electric field. Inductor like this will store energy inside the magnetic field. So when you turn them off, they collapse. And when they collapse, they're going to burp out the energy. So in the phone, I have to look it up. Okay, so that was for the transformer. What else? Okay, I have another picture I wanted to show you. So here you have a solenoid, you see? When you connect a solenoid, you see the magnetic field does not like that. Yes. Okay, because it's a good question. At the time of Faraday, there was no AC. They just had so Faraday is 1930, so it's the mid 19th century. So AC is Tesla. So Tesla comes after. So at the time of Faraday, they just invented the battery with Volta. Okay, so he had only available the the voltaic cell. So he could not that came after. And so talking about that, so his experiment was, and then I don't know when Tesla came. Maybe it was the beginning of the 20th century. Tesla. So that's Tesla who came up with the AC power supply because he had a very bad fight with Thomas Edison. You know, Thomas Edison, he said that AC was not good, that we had to stick with DC. And to prove his point, he took an elephant. His name was Jumbo, and he electrocuted the elephant in front of the TV. So not, no, and he did that also to dogs. So he was not the best. He was not a nice guy. He was a very good businessman. Um, because his point is, if you he didn't want to use a high voltage. So he say, look, if you use a high voltage, it's so dangerous. I'm going to electrocute these elephants using that. So it's all propaganda. I don't know. He had decided that maybe because he wanted to have the monopoly to provide DC to everyone, but that will not be possible. If you have DC, you need to be close to the power supply. You cannot transport electricity over a long distance. And he made all his um, strands, so he did everything he could to ruin Tesla. So Tesla was a genius, but he died. He died penniless. So he was very good at making money, but not very good, not a very nice guy. It's you can Google it, okay? It's the war between Thomas Edison and Tesla. Tesla never patented all his findings. Okay, so that's why he never made money because he was so passionate. He didn't want to get a patent. Thomas Edison was just the opposite. He had a patent here, a patent there, a patent there. And then if you try to develop his idea, he will go after you with a lawyer. He was terrible. I mean, in my opinion, maybe now he was a good businessman. So here is the experiment of Michael Faraday. So you see, you have your donut. It's made of soft iron. So you have a coil here that will be like the primary coil. And you see here you have a DC power supply. On the other side here, let's say you put a compass, nothing happens. So, Cora, to answer your question, that's the experiment. And you see, I'm going to close the switch, boom, and then it stops moving. I open the switch, boom, and then it stops moving. Okay, so it's during the time I close it, the magnetic field is going to expand, okay, and then it stops because the magnetic field stays and does not change with time. When I open the switch, it's going to collapse, and then nothing happens on the other side because once it reaches its maximum, nothing will happen. It has to change, right? So if I open, what's going to happen if I open, close? You see, I'm making AC. Look, I'm becoming a powerhouse. I'm producing AC. And you see on the other side, you get AC as well. Isn't it interesting? So the thing that you need to understand is that a solenoid, so you have an electromagnet, the magnetic field will expand. Okay, it will take time to be fully developed. Why? Because you are taking energy from the power supply and storing that inside the magnetic field. When the magnetic field is going to collapse, all that energy is going to be burnt out into a spark. That's the idea of an ignition coil or a Tesla coil. Okay, you have a huge discharge in voltage. Usually, it's not that as dangerous as a capacitor. Capacitor is the same thing. You're going to store energy into your electric field. When it's going to discharge, you can have a huge burp in current. Okay, that's how you can resuscitate the dead with a defibrillator. So likewise here, you see, magnetic field is storing energy. It's going to collapse, but it takes time. Okay, so during that time, you can induce current in a secondary coil. Isn't that interesting? So magnetic field is a way to store energy. Okay, so what else I wanted to talk about? Okay, so I don't know if you remember. So this is called the motional EMF. So do you remember we did that problem at the beginning of the unit? And you move, you have to pull it, okay? You have to do work. So this is a loop here. Okay, so a typical question for a final, for example, I have this loop here and I'm going to pull it. Okay, so I have to do work. I apply a force. And now what's going to happen to the magnetic field lines going through the membrane attached to this loop? The number of field lines poking through the membrane attached to this loop here, are they increasing, decreasing, or they stay the same? As you pull the square through it. Increase, very good. It's going to increase, right? So because the number of lines are increasing, I'm going to induce an EMF. Once it's there, and I'm still pulling it, is the number of lines changing here? No. Okay, it stays the same. So am I inducing an EMF? No. To induce an EMF, the number of field lines poking through the membrane attached to your conductor has to change. What about here? Is it changing once it's gonna leave this area? Yes, right? So is it going up or down? The number of field lines going through the membrane? Down, right? So it decreases. As long as it's changing, then there will be an EMF. Okay? Is that clear? So that type of EMF that you are inducing, it's called motional EMF because there is a motion involved. And the equation for that, we already we did one problem with this, will be the velocity. So you are pulling your square, will be the velocity of the square. This length here, that length, okay, which is parallel to the velocity times b, VLB. You can do the same thing here. So you have a ray, okay? Here you have a bar. You are pulling the bar. So the number of lines poking through this membrane is going to increase. You're going to induce a current. You're going to induce a voltage. And that will be the equation. The equation will be the same. Yes.
For the EMF, you said it will only produce an EMF if there's a change in the number of loop lines.
Poking through the membrane attached to the conductive loop. It's like poking through. No, because you are leaving the area. So for example, first you're going to have, I don't know, 1, 2, 3, 4, 5, 6 lines poking through, and then it's moving, and now you have only 1, 2, 3, then it's moving, and then you have 0. If it's moving in this area, nothing happens. Yeah. Okay, so now I'm going to introduce something very important, especially for the final conceptual question. How can we find which way the current is flowing? The induced current is flowing. Are you paying attention? Okay. So you remember the story of Mary Shelley? I don't know if you know Mary Shelley. She wrote a very famous book called Frankenstein. Very good. And what's the idea behind Frankenstein is that you create your own monster, right? So you create a monster and then the monster turns against you. So Frankenstein, I think he was the professor, but the monster, forgot the name, he turned against his creator. So it's going to be the same thing here. You're going to induce a current, but that current is going to turn against whatever gave rise to it. So for example, here, what gave rise to this current? Is the magnetic field increasing or decreasing? Increasing. You say, I don't want the magnetic field to increase. I want to decrease it. So you see, magnetic field is where? Into the board or towards you? Into the board. So you say, I'm not happy with those number lines increasing. Okay? I'm gonna make a magnetic field on my own that will oppose that magnetic field that created it. So you take your right hand, okay? So which way the current has to flow to oppose its creator? It's gonna be counterclockwise, right? Because if it's flowing counterclockwise, the thumb will be your magnetic field. So it's like creating its own monster that will oppose it. Why it has to be that way? Because that way energy is conserved. So that means when you're going to pull the square, it's going to be very hard. Right? Because you are converting mechanical energy into electrical energy using the magnetic field. Now, when it's inside, something happened here. Do you change the number of lines poking through the membrane? No, right? So nothing. And here, again, it's not happy. What's happening to the lines? It decreases. And you say, no, I don't want you to decrease. I'm going to help you now. So now it's going to flow in the opposite direction. So it's going to make a magnetic field that will help. You say, I don't want you to decrease. Right? So this is called Lenz law. So the current that will be induced will always oppose the change in magnetic field lines or the change in magnetic field. So if the magnetic field decrease, it will slow it down. Okay, it will oppose that. Okay, so this is called Lenz law. So we're going to talk about that. So here you have another way to induce an EMF. So this way, I didn't cover it, but it's just an equation. You can understand that from the previous unit. So look at the upper left here. Okay, so you have a bar, and you are moving. You are pulling the bar inside that magnetic field here. So these are made of electrons, right? So because the electrons are moving this way, the magnetic field is which way? Into the screen. So the force seems to be up, but because it's an electron, you take your finger down, okay? So electrons will build up here, okay? So positive there. So you are inducing a voltage, and this is called also motional EMF. And the equation will be the same, okay? Don't worry about it, okay? It's just if you have that for the MCAT, you can understand what's going on, or you can go to the textbook. If you need more details, you can go here. I found it's a YouTube channel called Physics Ninja. Ninja. Do you say ninja? 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 Okay. It's a good channel. By the way, if you are taking the MCAT or planning to take the MCAT, I highly recommend that you do the problems as we go along. So if we are doing induction, you should do the problem in the book, the prep book about induction. Okay, so we are talking about Lenz law. We are going to talk about Lenz law, but let's finish the unit first. Any question? Okay, so again, we were talking about transformer. So you have a power plant here. You have a loop spinning at a speed of 60 revolutions per second. You're gonna have you're gonna produce a voltage, 20,000 volts. You need to transport electricity to the consumer. So you have to do that through high tension line. And because you don't want to use too much energy because of heat, okay, because the wires have resistance, you need to bring the voltage very, very high. So the current will be very low. So you need to have a step up transformer, about 100,000 volts. And then it gets to this ugly thing, you know, at Sunny Eyes, just before the bridge, you have this ugly thing here. And that's where you're going to step down to about 4,000 volts. So you have a step down per transformer. And then before it gets to your house, you have still this ugly thing here that are transformer up the pole. Because in Florida, everything has to be above the ground. So this is so ugly here. And then this is also ugly. So you step down back to 240 volt, and then you can use for your appliances. So for example, if you have an audio system, maybe it's going to be 20 volt, maybe it's going to be 6 volt. So inside it, you need to have a step down transformer. Is that clear? Okay, so that's how the real life works. Application genius, Tesla, and Nicholas, I think first name, Nicholas Tesla. So for example, he did the Tesla coil. Okay, so the idea again, you're gonna have a step up transformer, okay? And here you're gonna charge a capacitor, okay? When the capacitor is gonna be charged so much that the voltage is gonna be very high, okay, so the capacitor will burp out. Remember, a capacitor can burp out current, a coil will burp out voltage. So the capacitor will burp out current, and the current will be so strong, it's gonna jump the gap here, okay? And you're gonna have oscillation back and forth. And here, again, you have a transformer and you're going to step up the voltage to 100 or maybe 1000 volt, right? 1000 volt, the current will be very small. Okay, so it's very small current here, very high voltage, and you can have a huge discharge. And in addition to that, he did it, but he didn't get he was not a good businessman, okay? He was able to make a wireless to produce electromagnetic wave without wire, okay? So to produce radio waves, but he didn't patent it, so it was picked up by Marconi. Okay, that I'm not even sure if Marconi gave credit to Tesla. So the guy was a genius. So that's how a Tesla coil works, right? So you remember the demo I did with the plasma globe? There is a Tesla coil inside. Because you remember, I used my computer to power the plasma globe. My computer is only 5 volt. So you go from 5 volt to 100 volt to get that plasma. So it's very smart technology behind. Okay, so this is another application. You all know about that. It's an induction stove. So do you think if you have a glass pot, do you think it's going to work? Right? You are inducing current. So underneath here you have a coil. Okay, so you have a coil and you have AC power supply. Okay, so the magnetic field will expand, collapse, expand, collapse. So it's going to induce current. Can you have a glass pot? Is it going to work? No, because it's a insulator, right? So only the metallic pot will work, like aluminium, okay? Because then you have a induced current, and if you have induced current flowing, that's going to be uh, hot, okay? You turn that into heat. So that's how those work. So this is I don't think it exists. It's just a prototype with those electric car that you could be charging, for example, just standing on a station. And here you have a huge coil, and um, and then you can charge your car. So you see, you can induce electricity in this coil. This coil will be connected to a battery that you can charge. I'm not convinced about that green because anyway, electricity or energy has to come somewhere, to come from somewhere. So I'm not sure it's really green, but that's just an opinion. But the physics behind it is interesting. Okay, here is another very nice application. You have some safety here that you can add to the outlet. So you see here, when the current I1 equals to current I2, one is going in, the other one is coming out. So they're going to cancel each other, right? But if somewhere there is a leakage, right, there is a short, maybe you plug your appliance and there is a short somewhere. So that means you're going to have more current out than you have in. So in that case, okay, you're going to have a magnetic field here, expanding, collapsing, expanding, collapsing. Okay, and the source will be the current here, okay, because there is a leakage somewhere. That will induce a current in this coil. So this will be like the secondary coil. And you connect that to some kind of electronic detector, and you know that there is a problem. So the circuit will open. Okay, you can buy that at Home Depot. Okay, it's like something that you add to the outlet to make sure that there is no short. Okay, is that clear? Is that interesting or what? Right? No one is spacing out over there? Don't space out? Okay, so now interesting stuff. It's called Lenz law. So the current, okay, so important for pop quizzes or final, the current that you're inducing always is going to flow in such a way that it will oppose whatever gave rise to it, right? So for example, you bring the north in. It's not happy. And I say, no, I don't want you to come in. Okay? So the current here, do you see? if the current is flowing into the screen like this, look at your thumb. The thumb will be to the left. Do you agree? So that will be the north. So that way, your coil becomes like a magnet, okay, like an electromagnet, and it's going to oppose the change in magnetic field. Okay, say, don't come. I don't want you. I don't like you anymore. Right? And then, I don't know if you know the song, Carmen. Do you know the Bizet opera? Um, if you love me, I hate you, and if you hate me, I love you. Okay, so it's same idea. So here you have the magnet here pulling away, and now it changes its mind. No, don't go. I was kidding. In fact, I love you. Stay, stay, stay. So now the current is gonna flow in the opposite direction, such as now you're gonna have the south to attract the north, right? So why is it happening? Because here, since now it's the north, you have to push. You have to do work. And if you want to remove it, okay, so that means the number of lines are going to decrease. You also have to pull. So that way, you do work, okay? So mechanical work, mechanical energy will turn into electrical energy. But you cannot have energy for nothing. You have to sweat. That's what Lenz law is about. Okay? Very interesting applications because that's how braking, the magnetic brake that you have for trucks work. Okay? It's based on conservation of energy. So that's why in your textbook, you're going to see a minus sign here. Do not worry about the minus sign. Okay? You don't need to take it in account because that will be Lenz law. So you can always figure out which way the induced current is going to flow. It's going to flow in a way that it will say stop. If you come in, no, I don't want you. Okay, if you are leaving, okay, I want you. Okay, so always trying to oppose whatever gave rise to it. Okay, so let's try to work this one. Okay, so it's a nice review. And in addition to that, you need to know which way the induced current is going to flow. So it's a nice review. A nice review. So now we are working for the final, okay? Time goes too fast. So help each other, talk to each other. Okay, more you work in class, less you have to do it at home. So do it. Okay, so you have magnetic field where? Into the screen. Do you all agree with that? And it's increasing. So that means the number of crosses here, it's going to increase with time. So maybe you take a magnet in your hand and you shove it toward the loop. So the number of lines are going to increase. Okay, so that means the magnitude of the magnetic field is going to increase, right? So you take your magnet, zoom into the screen. Okay, so go back to your big idea if you want. Make sure to find the right equation. Don't erase your memory. So the magnetic flux equals the number of loop B, A, and here there is a cosine, but we don't worry about it because it's going to be perpendicular. So you see, this is your membrane. Okay, and the magnetic field here is poking through the membrane, and it's going to increase. You're going to have more magnetic field lines poking through. Okay, so I give you time. Okay, I'm not doing it. I'm just drawing. So first you're gonna have maybe 2 lines through it, and then you bring your magnet in, and you're gonna have more lines poking through. Okay, make sure you help each other, blah blah blah. Cosine is 0. No, because you see, when you talk about the angle, when you are talking about the angle, you are talking about this angle here between the magnetic field and the vector perpendicular to the membrane. So if the membrane here is perpendicular to the magnetic field, alpha equals 0, cosine of 0 is 1. It's tricky. So EMF will be, so what is changing is B. Okay, it's going to be delta phi over delta T. So M is not changing, yes.
For the A, why don't you just kind of explain that if it says perfect, how does it always mean that it's 90?
No, no. The magnetic field is perpendicular to the plane. But that's not what we use in the equation. In the equation, we use the angle between the magnetic field and the vector perpendicular to the plane. Right? So even though here, for example, here, the plane is perpendicular to the magnetic field, but that vector makes an angle of 0 with the magnetic field. So cosine of 0 is 1. Because here they say the plane is perpendicular to the magnetic field. So when the plane is perpendicular to the magnetic field, that means you're going to have the maximum flux. When the plane is parallel to the magnetic field, the flux equals 0. And you can see it in the drawing here. You see the field goes into, right? So number of loop does not change. A does not change. So the only thing that changes is the magnetic field. So what do you get? Okay, number of loop is 1 times the area. So area will be pi r square. So it will be pi 0.1 square. Okay, so area pi 0.1 square. The rate of change of B is given to you. So multiply by 0.1. So what's going to be? Huh? It's going to be what? 2 pi. No, it's pi, so it's 3. We can do it in your head. Look, pi is 3. 0.1 square, that means 0.01 times 0.1. So that will be 0.001. So that means it's going to be 3 times 10 to the negative 3 volt, which is 3 millivolt. Yes? Everyone is clear? It's because it's a wire loop. If it was 10 loops, if it was a coil, so then you will put N equals to 10. So how can we find the induced current? We use Ohm's law. So will be EMF divided by the resistance. So it will be 0.003 divided by 2. And you get, yeah, so milliamps. About. Yes? So the number of field lines is increasing or decreasing? It says here. Increase. And the magnetic field is in the screen. So it means, you see, the number of lines are going to increase. Is it happy? Say no. Not happening. Stop. So which way it's going to flow? Very good. This way, right? It's going to be counterclockwise. It's going to flow this way. So it's going to make a magnetic field saying, stop, I hate you. Right? So it's going to flow this way. As long as the magnetic field is going to increase, you're going to have an induced current that wants to oppose its creator. If the magnetic field is decreasing, it's going to flow in the opposite direction. So that's why if you take a magnet, you go in, out, the current is going to flow in one direction, in other direction, in one direction, other direction. So that's why we get AC. Isn't that interesting? Right? Because one of the golden rule is conservation of energy. You cannot have energy for nothing. So you have to do work to produce energy, electrical energy. So you go from mechanical energy to electrical energy. I have too many slides. I'm totally lost here. Okay, so here, typical equation as well. So you have a coil or a conductor here. Okay, it's like a ring, and it's gonna fall here. And here it's entering a magnetic field region. So magnetic field into the screen. So in this time here, do you have an induced current before it's entering? No, right? Because the number of magnetic field lines poking through the area is not changing. And now what's gonna happen to the number of field lines? It's gonna increase, right? And say, no, I don't want you. I'm gonna say, I don't want you to increase. So the induced current will flow counterclockwise, opposing it. Then when it's going to fall here, nothing will happen because the number of field lines are not changing. And then when it's going to exit, is it increasing or decreasing? Decreasing. Very good. I say, I don't want you to decrease. I changed my mind. So, it's going to flow clockwise to support its creator because it doesn't want the creator to go away. So it's going to reinforce the magnetic field. Isn't that interesting? Okay, so this is called Lenz law. So you have something called magnetic break. So let's say you have a pendulum, okay? When it's going to enter the magnetic field, the change in the field lines poking through this pendulum here, okay, is going to change. And this is called eddy current. So these are induced current that will oppose the change in magnetic field lines poking through. And the result, that means that it's going to slow down. And the big truck You know, they don't have like a brake like cars have, because otherwise it will be too much heating. They have something like this. This is called a magnetic brake. So let me show you if I have magnetic brake. Yes. So it's a magnet. Okay, that's why. So it's a magnet on a pendulum. And here you have a piece of copper. So as the magnet comes toward the piece of copper, it's going to induce eddy current. It's going to induce current, and that current will make its own magnetic field. Okay, that will say stop. So it's like a brake. Ready? Look, poof. Do you see how it's braking? Poof. It's very weird. Look closely. It doesn't get to touch it. Do you see that? Isn't that weird? Right? That's a magnetic brake. Poof. Let's see. I have another video.
This pendulum. This is an ordinary pendulum, but it has a piece of copper at the end. And when it swings, the piece of copper swings between the poles of an electromagnet. But the magnet is not turned on right now. If the magnet were turned on...
So you see here, you have like a magnet. So anyway, you have magnetic field lines here when the magnet is going to turn on, because it's an electromagnet. So far nothing happens, right?
The poles of an electromagnet. But the magnet is not turned on right now. If the magnet were turned on, imagine what would happen. The piece of copper would swing into the magnetic field. Because it's swinging into the magnetic field, then by electromagnetic induction, electric currents would be induced to run around in the copper. Now, whenever currents run around in a piece of metal, that causes heating. And so there would be heating, and that means that energy is being lost from somewhere. But where does the energy come from? Well, the only place it can come from is the swinging of the pendulum. So the pendulum should actually slow down if I turn on the magnet, which I can do by closing this switch. So here's what I'll do. I'll get the pendulum swinging again, and you sort of get the rhythm of the pendulum swinging back and forth. And then when I close the switch, you'll actually be able to detect that the pendulum slowed down. Okay, so here we go. I'll get it swinging again. Watch it. I'm going to close the switch right now. Watch this. There. Did you notice that? One more thing I'd like to show you, and that is that not only can electromagnetic induction stop a piece of metal, it can get one going again. Because a piece of metal doesn't like to be in a region of strong changing magnetic field, which I have right here. If I take this ring of aluminum and put it down in the field and turn it on, you should actually be able to see the aluminum jump when I turn the field on. You ready for this? Here goes. Watch. There.
So when you switch on, okay, here you have a huge electromagnet. Current will be induced, but that current will oppose the magnetic field from here. Okay, so if this is a north, that will be a north too. So they will repel each other. Right? It's a very famous demo.
For this, here goes. Watch. There. Well, I can't do any better than that, so I'll see you next time. This pendulum.
Okay, so I got a demo for you. I just hope it works sometimes. And you need good eyes. Do you have a good eyesight? Can you see from here? Do you see it's a pipe and it has holes. Do you see the holes here? Right? So first I'm going to put a piece of aluminium. So a piece of aluminium, is it a magnet? Can aluminium behave like a magnet? No, right? So I'm going to place it here. and gravity takes over, boom. You see that? Okay, nothing special here. You can even see it falling toward the hole, boom, right? But now I take a magnet, a neodymium magnet, so it's a very strong magnet. What do you think is going to happen? It's going to almost stop, okay? So it means as it's going through the tube, it's going to induce a current here, okay? Because it's a conductor that will try to slow it down because energy of motion is turned into electrical energy. So it has to slow down. So let's see if it works. Ready? Boom. It takes forever, right? Boom. See that? So this is called Lenz law. So all the experiments I have are small, okay? Because, I buy them. And first of all, it will be too heavy and too expensive. But if you can afford bigger experiments, of course it's going to be better. Okay? So that's the best way to do it. So it's not a magnet. Okay, so now he's going to take a neodymium magnet, same size, and then it takes forever. So that means here you're going to have induced current, they are called Eddy current, that will slow it down. Oppose the field of the falling magnet. Oh, that's cool. See, I don't have the technology, but this is very cool. Ooh, do you see how it's floating? Right? Isn't that cool? Wow, very nice.
Kind of in a circle. Is that the way the current is going?
No, I think it's just because I don't know why it's going back and forth like this, right? So here, that will be the pendulum, that the demo. You see, current will be induced. That current, you see, when it's entering the magnetic field. So maybe I think it's a pop quiz like this. You see, the current is going counterclockwise, opposing the increase in magnetic field lines going through the plate as it's going to leave the magnetic field. The current is going to flow in the opposite direction, and then it says, no, I don't want you to go. Okay, I'm going to help you. I don't want you to decrease. Now, if you make opening there, it's not going to work as well because the current cannot flow. Okay, because you have too much resistance here in the air gap. Okay, so you have a lot of application. This is an electric guitar. Okay, so that's not Lenz law. I don't know why this slide is here, but the idea is that you see that string here get magnetized. So when you play the guitar here, it's going to push and pull here the magnet. So it's going to induce a current in here. The current will have the same frequency as the string. Okay, so that's why you turn the motion of the string into a AC. Okay, same idea here for a microphone. Okay, so you push and pull. Okay, so the coil is going to move back and forth. You're going to induce a current. That current will have the same frequency as the sound that you are making. so you can record your voice. You didn't just arrive, did you? You did arrive?
Got up there 1:30 to the joke like this.
Ah. Okay. Another application here, it's called the speed control. Okay, so your motor is spinning. You attach a magnet here. The magnet is going to spin at the same speed as your motor. Okay, spinning. It's going to induce a magnetic field here. And that magnetic field is going to change at the same rate. And so here you're going to induce a current, and so you can know the speed. And then there is a feedback, controlling the speed. So it doesn't go too fast. So it's called speed control. Okay, so that's super interesting since most of you want to go in medicine or biology. So there is this therapy. So I have no idea if it works or not. You can tell me. I don't know if it works or not. Okay, but it's a therapy using induced current. So your brain is soft, so it's a good conductor. So here you have one loop. Okay, so you have current flowing. It's going to be, for example, AC. Okay, so it's going to produce a magnetic field that will collapse, expand, collapse. So it's going to induce a current in the periphery of your brain. Okay, so it's electromagnetic induction, and apparently it will stimulate whatever it's stimulating, and it's used in neurology and it's for mental health. I should dig into more into that. I don't know. Maybe it's good. Okay, a lot of things are working with electricity in the body, but I thought it was interesting. Okay, so by the way, each time you are exposed, we are all exposed to those electromagnetic waves, right? So all the time you have a magnetic field because electromagnetic wave from the Wi-Fi, from your phone, this electromagnetic wave have a changing magnetic field. So that magnetic field that is changing is going through your body all the time, right? And so it's going to induce current inside your body. Okay, so it's induction. Current will be induced inside you because you are a good conductor. Is that healthy? I don't know. I guess no one wants to dig into that. Okay, interestingly, there is no research done really. So maybe they don't want to know. But that's why times to times it's good to disconnect, right? To remove all those appliances, although it's almost impossible. So there is a big talk about 5G because 5G, of course, has more energy. Cool. We all agree with that, right? 5G has more energy. So the magnetic field is going to be stronger. Okay. So the induced current will be stronger. I don't know if it's healthy or not. Okay. I don't know about that. And I'm not a conspiracy theorist or whatever, but I don't know if it's healthy. So if you want to stay healthy, you take aluminum foil, you put that on your head, and then no magnetic field will be able to go into your brain. It's like aluminum hat, right? Some people do that. There was a very good show. I don't know if you watch that show. It's called Better Call Saul. Have you seen this show? And so there is it's a very good show, okay? If you want to understand how lawyers work and law firm, and then you don't want to be a lawyer when you watch the show. But anyway, the character has a brother and he's very scared of electromagnetic waves. So all his inside his house, he has aluminum foil all over. And when he go outside, he's wearing a aluminum foil hat. By the way, if you don't want anyone to trace you, right? If you have your phone, you put your phone in aluminum foil, right? And nobody can track you. Like if you have a helicopter mom, for example. I am an helicopter mom, so.
Is that because it points out the possibility of Satan getting to it?
Yeah, so if you put a foil, electromagnetic wave cannot get in. So you're shielding it. So it's like actually it's a good question. It's a Faraday cage. Because it's not because of the magnetic field. So the magnetic field will induce current inside you. An electric field is also part of your electromagnetic wave. So electromagnetic wave, you're going to see that you have an electric field that will induce a magnetic field, that will induce an electric field, that will induce a magnetic field. So if you put aluminum foil, it's like a Faraday cage, and the electric field cannot get through. So the signal cannot get through, right? So if you want to go invisible, you put aluminum foil everywhere. So, so you see here, that's the electric motor. Okay, so here you have a power supply. Okay, and the loop is, so you turn electrical energy into mechanical energy. AC generator is just the opposite. Okay, so you have to use mechanical energy, so you make it spin, and then you get electrical energy. So you can use a motor as a generator, right? So of course that's what we have in the power plant, electrical power plant. That will be the amount of energy consumed, 100,000 watts. But you can buy that if you go camping. You can buy those crank generator, right? So you can still have some electricity even though you don't have battery or whatever. Sometimes it's expensive, but you always find cheaper ones. Okay, here is also very interesting application of Lenz law. So when you go through those gates, okay, they're gonna generate a magnetic pulse. So that means magnetic field increase and then decrease. So it's gonna expand and collapse. If inside your pocket you forgot something in metal, maybe your keys or a gun, okay, you don't want a gun, but let's say there is a gun or something in metal, the magnetic field here, because it's changing, is going to induce current inside your keys, say. So your pulse is going to take more time to collapse, okay? Because the induced current in the gun, for example, is going to produce its own magnetic field that will slow down the collapse of your pulse. So then it will say beep, 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 and you are going to be in trouble. But that's how it works. Okay, it's because of Lenz law. This is induction as well. It's when you want to control the traffic here. You can count, how many cars pass by. Okay, because somewhere here underneath you're going to have a coil. And when you go through here, there will be current induced in the chassis of your car, and then it will slow down the collapsing of the magnetic field, say. So it's all electronics. So it's another application. Inside your car, you have an ignition coil. So the way it works is that the battery is going to charge a capacitor very quick. It has to be the capacitor. You don't want to charge the coil because the coil, it takes time for the magnetic field to expand. The capacitor, you charge it like this instantly. So you charge your capacitor when you start your car. That capacitor is going to discharge in a coil, okay? And the coil will discharge here, make a spark, and that's how you have a spark plug, and you can burn your fuel. Okay, so this is a coil and you can discharge it. Very high voltage. And here you see, I have all the equation that comes from your book, Johnson and Cutnell, and you have a summary of everything. The thing I didn't cover, but I think it's coming next in the unit, is that you see you have energy stored inside the magnetic field. So that equation here will give you the energy density. which means if you take a magnetic field inside the coil, for example, you take a unit volume, so 1 by 1 by 1, that will be the amount of energy. So you can store energy inside the magnetic field, and it can burp out high voltage. You can store energy in a capacitor, like defibrillator. Capacitor will burp out a surge in current. Okay, so capacitor burp out current, inductor coil can burp out voltage. Okay, but it's the same idea. You are storing energy. Okay. Okay. Here, what you can do. So here you have a coil. The coil is connected to a AC power supply. Okay. And here you have a piece of metal. This is not a magnet, it's just a piece of metal. So it's going to induce, because here the magnetic field is going to change, expand, collapse, expand, collapse. It's going to induce eddy current in this piece of metal. What's going to happen to the piece of metal? If it's getting very, very hot, because all that current flowing inside, okay, eddy current, all that energy is going to go to heat. What do you think is going to happen? It's gone. So what's happening to a piece of metal when you heat it up? Very much. Yeah, it's gonna melt. Isn't that cool? Right? You can do art and craft, right, with that. So again, it's connected to a power supply AC. So the current here is gonna be alternating. Okay, so the magnetic field produced will be expand, collapse, expand, collapse. So it's gonna induce a current. All that energy is gonna go into heat, and it's gonna melt. Super cool. Very good TikTok video. And what else? Another very cool thing. Okay, I have 2 minutes to find. Here. So this is a Tesla coil. Okay, so the top here can be, so it means it can discharge in a very high voltage. Okay, and you have a syringe here, you have a nail, and that will be connected to the ground, I suppose. So this is called the plasma syringe, right? So you have a very high voltage. You're going to have a discharge because the voltage is so high that it's going to ionize the air molecule. Okay, so you have a spark here, and here it's also be ionized. Okay, and this is called the Tesla coil. You can buy them. They are cheap, but maybe not the safest. I don't know.